All right. So in this section, we're going to parameterize or teach you how to parameterize anything we want into different variables. Okay. And then we're going to find the areas of their regions given respectively. Okay. Now, the cool thing about this one is how we graph it. We go from 2D to 3D. It's a very interesting way of doing so. And it's how one special printer was actually created to do so. All right. So, but first we'll talk about this. So, but first, let's talk about, a U and a V. So we're going to usually use U and V when it comes to our variables. You can use any letters you want, U, V, W, if we go to 3 dimensions. Usually it's in terms of the letters right before X, Y, Z. That way no one gets confused, going backwards. But you can use A, B, and C if you like, right? It's just universally used U and V and U, V, W because of the last 3 letters of the alphabet before we get to X, Y, Z. Right? But again, it really doesn't matter. Okay, so how this is going to work out is, let's suppose we have X and this variable, this parameterization of X, Y, Z, where X, Y, Z is in terms of U and V, right, in each one respectively. Okay, so this is what's called a parametric surface S right here. So this is a parametric surface in S. Okay, so we have some surface that's being parameterized with these 3 equations. Okay, now the process how this works is each point of UV creates a point on the surface. Okay, so again, if I parameterize it going this way, so now this is U and V. So a point on here that's in some region D, let's just say it's a rectangle, for instance. So this point U, V. And if I plug it in, this now becomes a point on this surface. Okay. However, the interesting part of how this parameterization actually does work is we really haven't talked about why we do this. We talked about, okay, this just makes integration much easier, but we haven't talked about why this is so important and how interesting parameterization actually does work. Okay. Now, not only does it create a point on the surface of it, every point in D, when parameterized, so if we go through this R vector field here, gives us a point on here. Now, the interesting thing is not only does it give me a point, however, where I'm plugging it into a vector, right? Where parameterizes X, Y, Z. So therefore, I get a vector out at the point X, Y, and Z. It's an actual vector going to that point. Meaning if I pick another point here, and it goes here, I get another vector there. And each individual one gives me an arbitrary vector, right? It just goes all the way around itself. Now, this is what the cool part is. Every point on here creates the entire surface in such a way as if you're tracing it all the way around. And the best way I can think about it is like a 3D model or a 3D printer. So if you guys ever seen a 3D printer, or you can Google or YouTube a 3D printer, and you can see how it comes out. That's exactly what's happening here to there. Because what a 3D printer does is this is on a computer screen, and what prints out is the vectors of that computer screen, or in other words, that parameterization in 3-dimensional models. So you could think of like a typewriter, any point here goes tick, 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 tick. So it's literally just printing this entire surface out based off a 2D plane. And that's so interesting about parameterizations, exactly that's what's happening. We just haven't told you that that's really what's going on. Okay. But the cool thing is any picture here, you can make it into there. And that's how surfaces and printers are created in 3D modeling. So that's the interesting part is, what parameterization actually all it is. So I thought it was fascinating how that's created. You could sketch something in a paper and, plug in a calculator and print it out, and you'll get a 3D model based off your picture and based off your parameterization of R, right? I think that's pretty interesting stuff how it works out. And I give you guys an example right here, right? So here's our region D, and this point U represents that point there. And again, if I pick any other point, I'm gonna get vectors going off where it just like literally prints out in 3 dimensions the entire surface of it itself, which is pretty cool. So therefore, since it prints out, points and vectors, that means if we have lines in 2D, right, here's like, vertical lines going up and down, that represents curves and surfaces. So, right, so for example, this red curve represents C1 here. So instead of L1, this represents curve 1. And this line L2 represents curve 2. So if I do this, that represents a curvature from one end all the way to the other, bending like that. So you can kind of tell, boom, if I pick every point on this dot, this vector is going to completely trace the entire curvature of that. So you can kind of tell what we're about to do is, okay, this type of parameterization can give us a line integral in 3 dimensions. So I kind of gave it away, but that's exactly pretty much what we're about to do. Well, not in this one, but eventually as well. Okay. So I thought that's pretty interesting how that works out, math and actual application stuff. Okay. All right. So one fun little tell-all here. So I printed this, I didn't print this up, but I put this in a 3D modeling. So here's my vector. So this is my parameterization of U and V. So this is my presented as, right, X, Y, and Z. Right, so here's my parameterization, my vector, with respect to U and V. This is technically my point X, my point Y, and my point Z when I convert it to 3 dimensions. And when you do that, you get this figure here. So for those of you probably look at it, oh, cool. Like, maybe if you were a kid, you saw like a little swing, go all the way down, get out, you can do it again. For us horror majors, if you want to know, this probably looks like a Resident Evil. This is a T virus. If anybody knows some Resident Evil stuff, right? So it's a T virus portion, right? So if you just cap it here, that's exactly the T virus or all the other viruses from Resident Evil portions, right? So the cool thing is, right, this parameterizations give us a 3D model of stuff. Okay? Or if you're into biology, this is the half of the part of the DNA strand. So if you guys are wondering, why math is so important, how, this is actually played, math actually shows you a model of what DNA actually looks like mathematically, right? And that goes into genetics, and that goes over my head, but it's part of how genetics is actually created, which is cool stuff, right? When it comes to it. If you can find a model to it, or you can find a function, therefore you could tweak it. And if you could tweak it in the theoretical, then it goes back into, can you tweak it, practically? And that's where all the experiments come into play. But my theory is, it looks like a T virus, so may have to put some Resident Evil background noise into this so you can see how evil mathematics can actually be, right? But anyways, a little fun there. Now, how do you parameterize a vector field, or just itself, okay, a function? So there's roughly 4 different ways to do it. And it's pretty much using all of the ways we know. There's nothing brand new, which is the nice thing, okay? The first one we know is a cylindrical, right? So X is equal to A cosine theta, Y is equal to A sine theta, sorry, and Z is equal to Z, right? We learned that a couple sections ago. The hardest one, and I guess the ones you guys probably hate the most, is the spherical. It's because in terms of phi and cosine, I'm sure you guys love that section as much as you possibly can, right? And then it goes, the last ones are the easiest ones. Now, number 3 is the most simplest. So whenever you see that, or someone tells you it's the trivial representation, basically means X, Y, and Z is just itself, X, Y, and Z. But the only thing is Z is in terms of X and Y. That's called like the trivial, because you're not really doing much there. And it's the simplest one to do so. Most of the time, it won't work out. You actually have to convert to one of the other 3. But, usually that would also work out as well. And then the last one is, everybody's favorite, the polar, because that's the easiest one to convert to all 3. It is, again, R cosine theta, Y is equal to, this is supposed to be R sine theta, and Z is in terms of R and Z. So simple little examples of, given these type of functions, let's just parameterize it, right? So using one of these four, they just, convert it, right? Now, for a lot of these, you can have multiple conversions. And that's the cool thing is, even though there are multiple conversions, you get the same result no matter what, which is, kind of nice, right? Well, technically you should, right? Whatever you parameterize, you can get something else out. So, for example, we're going to do two of these. So for the first one here, I'm going to do it twice. Okay. So first one, I'll show you the trivial one. The trivial one is we're just going to x equal x, y equal y, and then z equals in terms of x, y, and z, right? So this is in terms of x and y, which notice it's already done for us. Ta-da. Easy. Hence why it's called trivial. Now, the reason why we cannot use this all the time is because notice one variable, it was already done for us, right? It is all equal to each other. Unlike over here, which I'm going to give you anyways, if we solve for one of these variables, I'm going to get a plus or minus because of that square, which means that parameterization from here to here won't work. Okay. So whenever you have a variable equaling something, or it's very simple to solve for one of the variables, that's when you can use the trivial one or just the x, y, z one. Okay. Now, the other way we could do it is the other easy one, polar, right? So let r equal r cosine theta, let y equal r sine theta, and let z equal exactly this. So be 3 square root of r cosine theta minus r squared sine squared theta, right? That's another conversion we can have as well. So again, two different ones, that's still technically a parameterization, right? You just change the variables. And then B, as you notice, you've probably seen this, right? Whenever you have x squared, y squared, z squared, that always gives you a sphere, right? So easiest conversion is just giving you that. So in this case, our sphere, right? A is going to be the radius of the sphere. So it's just going to be 3 in this case. So x is going to equal to 3 sine phi sine theta, or sorry, cosine. Let's cosine. Cosine theta. Y is equal to 3 sine phi sine theta, and then z is equal to 3 cosine phi. So just a simple example showing you how to convert, right? We've been doing this for a long time. You just didn't know, that's what's called parametric representations and how they look like in 3D models, right? So, it's too hard to graph it manually, but, we use computers now to easily show what we're actually looking at and tweak it from there. So now you can go home and say, or you're home say, I know how to do a T-virus manipulation now. And so then you guys will create the zombie apocalypse. Don't blame me though. I'm just the messenger. Anyways, tangent planes. All right. So, like I talked about yet a couple of minutes ago, right? I can create curves using this transformation, right? So this curve here represents that curve. This curve represents this curve here. So therefore, if I can represent curves in 3D models, therefore I can find tangent planes, right? Going back, way back to what we did, right? And remember, the tangent plane itself represents all the tangent lines at the single point here, right? So it's going this way, that way, all the way around, right? Here, here, here. Any single tangent line goes through it, represents a tangent plane, meaning all those tangent lines are represented as a plane at any particular point. Okay. Now, just in case it's been a while, because I know it's been a while, you forget how to find the tangent plane itself or the tangent vector, right? Is quick little note here. So the tangent plane is the cross product. And this is a normal vector. Okay, that's what we're going to be using. So just in case you guys forgot how to find tangent planes. So given two tangent lines, right? That's RV and RV. So the tangent plane of this one, tangent plane, right? Those are my tangent lines. So the tangent plane, remember how to find a plane? We need a normal vector of two vectors, which is just the cross product, and then we just plug in the point. We're going way back. So this is what I mean by if you're on your final, right? If I can give you 4 questions, I can ask you find the tangent plane of this, and this describes 4 different topics, right? Knowing this section, how to parametrize, knowing that you need to find 2 vectors, and now knowing that the cross product is gives you the tangent plane, right? That's 3 or 4 different topics in one question, right? So that's where you go for your final. It's only 4 questions because of that. Okay? Just in case you guys are wondering how I would put stuff together. Okay? All right. So in that case, let's try a practice problem. All right. So let's find the tangent plane to the surface with parametric equations: x equaling 2u squared, y equals v, and z is equal to 3u minus v at the point 2, 1, 2. Okay. Now, before I go any further, because I know you may skip this step or forget about this step. We're going to get the vectors from uv and ur. Okay, so everything is going to be represented in terms of u and v, not of x and y. Okay, so when we get our tangent plane, and when we get this cross product, it's going to be in terms of u and v, not x, y, and z. Okay, so therefore, this point here is in terms of x, y, and z. So I need to find what u and v are going to be respectively based off those points. Okay, how we do that's very simple. If x is equal to 2, therefore 2 is equal to 2u squared. If y equals 1, so therefore y is equal to v. And if z equals 2, therefore 2 is equal to 3u minus v. Okay, and now we just solve for v and u respectively. Then notice the nice thing is 1 is already done for us because y was equal to that value itself. So now we're just going to find u. And for that, you can just plug it in. You can plug it into here. So that's just 1. And you're solving for u. So adding 1, it's 3. So u has to equal 1 as well. And it works, right? So plug in u squared. So 1 squared gives you 1. 1 times 2 is 2. Check. It works out. So we have at the point 2, 1, 2, the x is y, x, y, z. Those points give us a u and v of 1 and 1. That's a key thing, right? So this is the point in the 2-dimensional plane that represents that point in the 3-dimensional plane. All right, so we'll use this later on, but just for now, we'll put that to the side. Let's go back over here. Okay, so R of u. So remember, that means is we're going to find the derivative of our vector in terms of each one respectively. So the derivative with respect to u, and u, then v. Okay, so R of u is the derivative with respect to u, so that's just of x is just going to be 4u I plus the derivative with respect to u, which is going to be 0, so 0j, plus the derivative with respect to u, which is just going to be 3. Okay. And now we do the same thing for v. Okay, so the derivative with respect to v is going to be 0. Derivative with respect to v is going to be 1. And the derivative with respect to v is going to be -1. And now we're going to find the cross product. All right, so this cross product is going to be, if I do this way, 0 minus -1 is 0. 1 minus, or 1 times 3 is 3. J, 4u times -1 is -4u. Minus 3 times 0 is 0. And then finally, that's just going to be 4u minus 0k. So therefore, our tangent plane, or a normal vector, right? This is the normal vector. This is a cross product. Be negative 3i plus 4u j, and this is going to be plus 4u. Okay. So now this is why we needed u and v, because notice, a lot of stuff cancels because it's a nice derivative, but we still have u's here. So now we're going to plug in our point v1 and u1 and gives us our actual vector in terms of just numbers. So it'll be negative 3i plus 4j plus 4k, because u is 1. So just 1 times itself is just itself. So therefore, our equation for our tangent plane is going to equal to negative 3 times x minus 2, because now we go back to the x values, right? This is just a parameterization, plus 4 times y minus 1 plus 4 times z minus 2. And this is our tangent plane right there. Questions at all? No, all good. Okay. All right. Last topic, area. More importantly, surface area. Okay. Now we talked about this whole thing traces something on the XY plane, right? Now let's think of a box. So what does a box look like in 3 dimensions, right? So given a box, given a region D, and I just break it up into like simple rectangles or squares, what does that look like when I plug it into our parameterization and go into 3 dimensions? So remember, this ends up being a curved box here, right? So let me curve it a little bit. Right, it's not completely a rectangle, it's a curvature. Okay, so if I just spew this out here, it's going to look something like this. Right, some bendy stuff. Now, this line here and this line here go to vectors here and vectors there, right? Going here, the vectors there, the vectors there. Well, that represents something going like this. We'll call that RV. And this goes this way. We'll call it RV. Now, we have actually talked about this way back in the day as well. Okay. So if we want to find the surface area, right? Surface areas mean we find an area above it. So just like the flat, like the surface area of this paper, is just the area because it's what's covering it, right? But if it's bendy, we want for surface to go up and down and curvature left and right. Okay. Now, this goes back again to a topic way, way, way back in the original course. How do we find the area given 2 vectors? Well, anybody remember? That's a good question for the final, right? Give you a hint, it's a parallelogram. It's the magnitude of the cross product. So when we do this parameterization, this area is what we get here, is an estimation of just finding the area of this parallelogram in vector format, which is exactly just the magnitude of the cross product. And for now, it's the best way to find the surface area of a surface in 3 dimensions using its transformations or parametric transformations. Okay. So therefore, if you want to find the surface area of all of this, right? So that means we're going to take the double integral, or sorry, the double sum of u's and z's of this magnitude of this cross products all together, where delta u and then delta v changes, right? And then how big we want our if it's circle, not circle, if it's rectangles or squares, this is going to be our surface area. Put surface area for short. So what I'm trying to get to is, we have actually done this before. We just haven't defined it. So everything we've done already is the same, right? Nothing really brand new. All we're doing is describing what's actually happening in 3D modeling. So notice dot product, cross products, tangent lines, all that describes stuff what we actually wanted to use, right? Instead of just going backwards. Oh, before we do this, we got to do this. Before that, we got to do it. Well, here's the biggest things, but notice it's just accumulation of what we've done before, the little bits and pieces of it. So therefore, since it's a double summation of it, we get our definition of surface area. If a smooth parametric surface S is given by the equations where X, Y, and Z are represented as U and V, therefore our surface area is the double integral of the region D in U and V, right? The region D itself, of the cross product of the vectors U and V. That's it's the cross product of R with respect to the partial derivatives of U and V. Now, if we do the simple parametric or the trivial one, right? So maybe basically X, Y, Z is our parameterizations. Therefore, our surface area is going to look like this. Okay. Where you could see maybe polar is probably going to be the way to go. Little hint there. Right? So sometimes this is why sometimes the trivial one isn't the way to go, because notice this is actually a little harder to deal with than this one here itself. Okay. But we're going to do examples of both of them anyways. So let's try an example of the trivial one. So when is this going to happen? Because, believe it or not, we have no choice but the parameterization anyway. So, you don't get around it anyway. So that's the sad part. All right. So let's find the surface area of the surface that lies under the plane z equals 16 and within z equaling x squared plus y squared. Okay. So this is kind of like a in 3 dimensions, like that. So here's my plane z equals 16, and it just goes like in an oval shape around. Right. So you can kind of think of it like a cup that has no flat surface, right? It's just like bendy. Or an urn, if you want to call it, right? That's pretty much where you're trying to find the surface area of the urn, okay? Where it's flat on top. Okay. All right. So we're going to use a trivial one here. Okay. So C equals X, we'll say X equals X, Y equals Y, and then Z is equal to X squared plus Y squared, right? Just like we did last time, just a trivial one. Okay. All right. So we're going to follow what we did above. So we define dz, dx, and dz, dy. So we're going to take the partial derivative x, partial derivative y. So I'll just put cx for short. So this is just going to be 2x. And then dy is going to be with respect to y, so it will be 2y. Okay. So plug it into our formula. So it's going to be the double integral over the region. We don't know the region yet. That's the reason why I'm not doing it yet. Of 1 plus this squared plus that squared. So 4x squared plus 4y squared dA. Okay. Now, before we go any further, again, before we do regions of bounds and all that fun stuff, do I really want to find the integral even with respect to x and y? I seriously doubt you want to, right? And again, some of these integrals are almost impossible to do, right? So that's why the hint is, right? Whenever you see x squared, y squared, what are we gonna do? Polar. We're gonna go straight to polar. So help us out. All right, so we know what x and y is. So what we gotta figure out is our bounds, r and theta. Okay, so theta is the easiest one, as you could tell, right? If we go if we use our circle just here in general, right? A radius is going to go from there to there. That's r, and theta is going to go all the way around. So that's going to be from 0 to 2 pi, right? That's the easiest one to deal with. Now let's look at r, the radius. So you plug in into here. So we know, oh, sorry. We plug in 16 in for z, and our polar coordinates into here, we get r squared. So therefore, r goes from 0 to 4. All right, so now we got that. Notice we didn't have to deal with the d because we went straight to the polar. That's the reason why sometimes it's not worthy trying to figure out x and y and just, brute force your way through it. Sometimes it's much easier just to, change some stuff. Hence the reason why polar coordinates was actually invented. Okay. So again, quick little note, right? X squared plus y squared equals cosine squared plus sine squared gives you 1. So we just get 4r squared. And just don't forget we have the simple r on the outside because it's polar, right? We have to multiply by that r value at the end. And now we can actually use u substitution. So then du is going to be 8r dr. So dividing by 4, or sorry, divided by 8 actually, is going to be 1/8 du is equal to r dr. Okay. So therefore, this is going to be the integral of u to the 1/2, which is the same thing as u to the 3/2 power, and this is going to be 2/3 there, right? So putting these together, this is a 1/8 out here. This is going to be what? Divided by 2, so that's going to be 4. So it's what, 1/12? I think, no, 1/12. So 1/12 of u, so it'll be 1 plus 4. We'll do that later. So it'll be 1/4 evaluated x, 1 plus 4r squared, with 3/2 value at 0 and 4. Okay. All right, so plug in 4. You get 16. 16 times 4 is 64. Plus 1 is 65. So we get 1/12, 65 to the 3/2 power. Plug in 0, we get 1, so just 1. Okay. And don't have this one out yet, so let me do this calculation for you guys. So I get 43.59 once I divide by 12. So then now becomes the integral of 0 to 2 pi of just that number. D theta. Which is, that's a simple integral, so I just double it. So 43.59. So 87.18 pi. And there we go. Questions there at all? Yep, not too bad. All right. In that case, let's go on to our last example. And this one's a doozy. All right. Okay. Find the surface area of the sphere of radius 5. Now, there's no equation given to us. However, we know it's a sphere. So it's you guys' favorite and my favorite as well. I say that sarcastically. Okay. So it's going to be equal to that. Good. Okay. So how do we do this? Well, everybody's favorite sphere. So our R of t is equal to our normal transformations, right? So x is phi, or sorry, rho, so it's phi, it's cosine theta. This is the I component, and the y component. Gives us that. Okay. Okay. So now we need to do, here's my equation here. Here's my equation. We need to do this one. Now, we go back here. We have 3 variables. We only need 2. So 5, remember, is equal to x squared y squared plus z squared. So we get phi squared is equal to 25, which means phi is equal to 5. So we can just plug 5 into here. So now it's only in terms of 2 variables, the 2 angles we're looking for. Okay. So that's how we're going to do this question now, right? So in our case, we're going to let u make it easier. This is going to be our u, and this is going to be our v in this format here. So we're still going to do the cross product and everything, but that's how we do our partial derivatives. Okay, so I know this is a lengthy question. So we're going to have r of phi first, then r of theta. So we're going to take the partial derivative of each one individually. And remember, phi is 5, right? In this case. So we're going to have partial derivative with respect to this one right here. That's a constant. That's a constant. So derivative of sine is going to be positive cosine. So it'll be 5 cosine phi sine. Or sorry, cosine is both cosine. Cosine theta. Okay, that's the ith component. Let's keep going. So again, same thing, right? It's going to be 5 cosine phi. This is the same. Okay. And then finally over here, this is going to be the derivative of cosine is going to be negative sine. So this is going to be negative 5 sine phi. All right, now we go back here. Now in terms of theta. So this, and that's, you know, it's going to be 0. Okay. So derivative of cosine is negative sine, so it'll be negative 5 sine of phi sine theta. Here, now it's in terms of this one, so it's going to be positive. So 5 sine phi cosine theta. And the nice thing is this with respect to theta is 0. That goes away. Okay. Now let's do the cross product. So it's going to be 5 cosine cosine negative 5 sine sine 5 cosine sine 5 sine cosine, and then k Okay. All right. That times that is gone. So we have that times that. Okay, remember, it's this times this minus this times this. So minuses go away, gives you positive. So what's left over is the multiplication of these two put together. So you get 25, this stuff. So we get sine squared phi cosine theta. All right, minus. It's like a J. Notice as well, that goes away. Okay, so we get a minus. So this times this minus that times that. Minus minus goes away. So we still have one minus left over. 25 sine squared phi sine theta. Okay, and now the last component is K. That's the worst one because that one we actually put some stuff out, right? So be this times this. So 25 cosine squared theta cosine phi sine phi. Minus minus goes away, so we get plus 25 sine squared theta sine phi cosine phi. This is the K component. Okay, now I'm going to do a little trick. Just bear with me. Okay, if we factor out 25 from both, and if we also factor out cosine phi and sine phi from both, we're just left with cosine squared plus sine squared. And cosine squared plus sine squared just gives you 1, right? So this whole part right here ends up being 25 cosine phi sine phi. Right? Pretty good so far? Okay. Now, you may think this is going to be the worst part because we have to find now the magnitude of it. It actually cancels out kind of nicely. All right, remember, the magnitude is each one squared being added together. Okay. All right, so 25 squared is 625. I'm just going to square everything, right? So that's pretty much what's happening. So I have sine to the fourth, cosine squared theta. The minuses doesn't matter, right? So just go away and just square it. Okay. Same trick. What this is for. That one. Yeah, square. Right. If I factor out these two things only from here to here, I'm left with cosine sine squared. Also gives you 1. Right. So I'm just left over with this. From all this is just that. All that goes away. And I attach this down here. Okay. Okay. Let's factor some stuff out. if I factor 625 from both of them, and I also factor a sine squared phi from both of them, over here I'm left with sine squared phi. And over here, I'm left with sine or cosine squared phi. Now, it doesn't matter what angle it is, the property still holds. Sine squared plus cosine squared equals 1. So this ends just being the square root of 625 sine squared phi, which just gives you 25 sine. Oh, so much nicer, right? So after all of this work, we're still not done. But we did the hardest part, trust me. Next step is literally just 2 steps. Okay. Now, what was our goal? Remember, our goal was to get that. So now all we have to do is take the integral over the region. And since everything is in terms of theta and phi, and since this is just a circle, that means theta is going from pi to 2 pi, and phi is going from 0 to pi, right, by its definition. So this is going to be the double integral from 0 to 2 pi and 0 to pi of 25 sine phi d theta. Now, the reason why I said this is so simple, well, what's the integral of sine? The integral cosine. Evaluate at 0 and pi. Well, if I plug in pi, that's -1. So this is being positive 25. If I plug in 0, I get 1. So this ends up being -25 times another negative here. Gives me a positive 50. Cool. So now it's going to be the integral from 0 to 2 pi of 50 d theta. Now would you look at that? That's just 100 pi. There we go.